Is my screen visible? Kindly confirm. Yeah, thank you. So yeah, we'll start in just a few more minutes. Hello, am I audible?
Yes, sir. Audible.
Yeah, hi Manish. So, I welcome everyone here. We'll be starting with the session now. And I just wanted to let you know that towards the end of this session, somewhere I'll be sharing a feedback form link, which will also be a certification form link of this webinar, where you will be able to get a certificate out of this. And when we talk about like aerodynamics, right? So let me just give you a brief overview of what we are going to talk about in this session. Yeah. So we will be starting with just a basic general idea of what aerodynamics is. Then we'll talk about aeroplane aerodynamics, how basically airplanes fly, and then we'll move on to the critical point where let's see how Boeing implements that in their latest series of 787 Boeing aircrafts. Yeah. So I'll just start with the session. So to remind you all, this session is a part of a series which I'm doing, where I'll be talking from subsonic to supersonic flows, and it will give you a general ideas about what kind of applications are there in this flow-wise regime, like subsonic flows, supersonic flows, hypersonic flows, right? So that way you will have a better understanding of the application part of it. And yeah, let's start with the session. So, can anybody tell me when it comes, what comes to their mind while when you think of Boeing 787? First of all, let me know how many of you have heard of or know about a Boeing 787. Yes, Dhruv, go ahead.
I hear. I know about Boeing 787.
Okay, can you elaborate what do you know about Boeing 787, Rupali?
Actually, sir, as a flight operation officer, I already selected in
Uh
Indonesia,
huh.
in Jakarta, in Jakarta,
Okay.
as a flight operation officer.
Wow.
Yeah.
Great. So it's nice. So anybody else? I think Dhruv had raised a hand. You mind? Okay. So Manish, yeah, you can unmute yourself and tell. Manish, am I audible to you? It's a long-haul subsonic commercial aircraft. Vedant says it's a long-haul subsonic commercial aircraft. Yes, exactly. Yeah. So it's great that you guys know about Boeing 787, right? So, like in general, Boeing aircrafts, right? So, to talk about the background and to talk about the history of like airplanes and how they fly, right? We'll be talking about aerodynamics of airplanes, why do we use airfoils, how does it generate lift? Then we'll exactly see how it is implemented in the flight dynamics of Boeing 787 to be specific. Yeah. So when you talk about aerodynamics of an airplane, right? The first thing that comes into play is aircraft has two kinds of motions, right? In order to fly, it needs to have a certain set of certain motion in order to like get that momentum going, and then it has the biggest influence, like in aircrafts there are the wings, right? These are the biggest influencing parts that generate a lift in the aircraft. So essentially when you are moving an aircraft, it will be provide the aircraft engines will provide the thrust that it requires to move forward in the to achieve a certain speed, and then the wings are adjusted in order to generate the kind of lift in this scenario, right? Now, why when we talk about this aircraft lift, right? So there is a phenomena in those wings. There are small sections that are being used they are called as airfoils. So if you take an aircraft and if you slice it over here, and if you see the side view of it, right, you will be able to see a shape that is constant throughout the aircraft, but it actually has different sizes. In which basically towards the end of the aircraft, as you can see, towards the end of the aircraft, the size is smaller. As you go towards the body of the aircraft, the size goes on increasing. Also, the orientation of those airfoils, as you can see over here, is a bit different, right? So why is it different? So why is it like that, right? So we'll see about the aerofoil part first. Now, these aerofoils are used for generating the airflow, right? Generating the airlift, basically. Now, how they generate lift is air will flow from the bottom of this aerofoil as well as from the top of this air, right? And essentially, this aerofoil basically generates high pressure at the bottom of this at the bottom space. The air that is moving below the aerofoil is moving at a relatively slower speeds. No, sorry, relatively slower speeds that generates higher pressure. And from the top of this aerofoil, the air flows at a higher speed, which basically generates lower pressure. And due to this difference in pressure, you will get a bottom force, like you will get a upward force in this direction due to the pressure difference that you have. So due to that, basically it allows the airplane to take off, right? So let's see how it generates lift, right? So it uses this Bernoulli's equation in order to utilize in order to generate that higher and lower pressure difference, essentially. So when you are moving from a streamline point, basically you're trading pressure with velocity. When your pressure increases, your velocity reduces. Where your velocity increases, your pressure reduces. That's basically the baseline bottom line of the Bernoulli's equation. And this is the most convenient form of the Bernoulli's equation, which is used to identify this phenomena and is being used in the airfoil lift, right? So how it happens, right? How the pressure loading happens. So basically, when you go into depths of understanding how the airfoil generates lift, or how the higher pressure regime is generated at the bottom of the airfoil, how it is generated at the top of the airfoil, you need to first understand the uh, pressure and its perspective. So when you talk about positive pressure, that means you are applying a pressure on certain body. So basically, that's the general nomenclature a positive pressure is identified for. So this is really important for us all to understand, because later on when we talk about how the distribution of pressure is being done on the airfoil, it is really important. So when a system is being in place of a surrounding, right? So when a surrounding exerts some amount of pressure on the system, then that pressure becomes positive pressure, and vice versa applies. So if a system is exerting pressure on the surrounding, then it is a negative pressure. Yeah. So that's the general context you need to understand from this base point. Yeah. Now, when you now when you are talking about this pressure, right? So when your system is being acted on, like pressure is acting on the system, then it is relative to atmospheric pressure, because it acts into the surface. And when you talk about negative pressure, so you can think of it as another way where a suction is being generated by the surrounding on the system, where there is a negative pressure forms above the surface, and essentially the direction of the pressure becomes from system to surrounding. So that's the context it is. Now let's divide the aerofoil into two parts. Like first we study the uh, top side of the activities, right? So when you talk about the top side of the flow, like flow over the airfoil, so due to the shape of the airfoil, like this nose shape, your your flow accelerates basically around the maximum thickness and then decelerates. So when your air is moving past this airfoil from this point, just use a highlighter. Yeah. So when your air is trying to move past this point, so at this thing, thickness of the aerofoil, the air is basically the flow accelerates and it attains the velocity. Now, when you have higher velocity, in turn, as Bernoulli says, your pressure becomes minimum. And as you can see over here, your pressure is in the upward direction. That basically means there is suction generated. That means this whole area is your lower pressure region. Basically your system is the pressure flow of pressure is moving from the system to surrounding, which is opposing to the atmospheric pressure. Essentially that means that your atmospheric pressure is reducing, right? Your overall pressure is reducing in that region, right? So that's what happens when the air is trying to move past the uh, top section of the aerofoil. And this is how it is designed intentionally in order to generate the lower pressure at the uh, top side of this airfoil. Yeah. Now, when you talk about the bottom area, so you will have your velocity that is moving in this surface or opposed to this shape. Now, the shape is also calibrated in such a way that due to this region, right? Due to basically you will have your flow accelerating at this point as well because it's just a minute. Yeah, basically at this point itself because it's still like bend kind of a way where it essentially bends the air that is moving trying to move past this point, and kind of gets throws off. So basically that's why your is negative. It's acting from the system to the surrounding. Yeah. When it tries to move past this point, yeah. So here the thickness is reducing. Also the curve is in such a way that your air then the accelerated air then tries to push or tries to move past this region, in turn generating an uplifting force at this region. And this force basically is applied in the form of pressure. Because pressure is nothing but force per area. Yeah? So this region basically generates the lift in the airfoil, and this lift, when it's sufficient to um, counteract the weight of the airplane, it essentially tries to lift the airplane off the ground, and that's how this phenomena works. That's how the airplane tries to fly. So in order to generate that pressure, in order to generate that momentum, you first need to move in a straight line direction. That is, you need to have the momentum going for your plane in order to have that air moving past this aerofoil at that velocity. Accordingly, that velocity will basically be converted into the kinetic energy that is generated is basically being converted into the pressure energy, and that's how the lift is being generated. This is how it is calibrated. Yeah. So that's how the general airfoil works. This phenomena works. So anybody have any questions at this particular point? They can ask me. Means pressure above the airfoil is negative suction, which is away from the surface. Yeah, yeah. Vedant says, sir, 70% of the lift is generated by the upper surface of the wing. This is the primary reason why engines are mounted below the wing. Yeah. So, see, the phenomena here that we are talking about is lifting phenomena, right? So don't think of this as a simple aerofoil structure, because there are sections in airplane wings that are basically like this aerofoil section is there, is being basically attached to the airplane, right? So you can see over here, just a minute. Yeah. You can see over here. So these are the sections. Yeah. So these are the sections that are calibrated, or that are basically divided into. This is a set of aerofoils that we are talking about here, and those aerofoils are basically used to generate that lift. So I'm just trying to explain how the exact phenomena works. because of the lower pressure that is generated on the top of this aerofoil, that is actually a major contributor. That's how the higher pressure at the bottom of the aerofoil is being able to push the plane upwards. So this is the general idea that I'm trying to give, so that basically becomes clearer for everyone. Yeah. Yeah. Uh, are there any other questions? This next part that I'm going to talk about is going to get a bit complicated. So if anybody has any questions at this particular point, they can ask. Okay, as the negative section created above and below the leading edge is its consequence. Um, the consequence of it being that it generates drag on the airplane, and it's basically you need more fuel, more power in order to counteract that drag by providing more thrust to the airplane. So that's generally that's how the airfoil structures are being optimized or are optimized in order to widen that positive pressure gap or positive pressure lift that we have talked about. So it actually depends on the shape of what sort of structure you're talking about. Yeah, is only airfoils, but there are a few minor changes in airfoil design, which are basically kept in consideration while different pressure requirements. So that's how they are utilized. So yeah, for it is the optimum design which basically is capable of generating higher lift. Vardhan asks, how does the stagnation point change with change in angle of attack? So basically, there are yawing mechanisms or rolling mechanisms are installed where you can actually change the. That's how the sections. That's why the sections of the airfoils are being made. So basically, when you talk about these structures, right? Let me just revert back over here. Yeah. So when you talk about these sections, right? So this is the purpose why they are basically divided into sections. Because as the angle of attack changes, you actually need to calibrate your wings in that direction. Accordingly, your aerofoils will be set, and accordingly they will be able to generate lift. So this is how, like, basically when you are basically gliding through when you are landing on the ground. So that's how there also it is being used where the different configurations are you buy with the help of computers. They are optimized in order to sense the angle of attack, and accordingly the airfoils will be adjusted, and that's how they actually optimize.
Hemant sir, can I ask you one question?
Sure, sure.
Boeing 787 intended to replace 767, right?
Yeah,
Exactly, I'm asking.
yeah, yeah, yeah,
787 intended to
yeah.
replace 767 or something.
It did was basically when the actual capabilities of we talk about Boeing 767, the
Replace
actual material
7.
that was being used in manufacturing that, the wing shape, the wing size was a lot more different. And when they upgraded it to 787, they actually used composite fibers, which are integrated with plastics, and that's how that's the biggest reason the 787 series has been a big success. So I'll be talking more about that as I move forward, but to get through these simple concepts, we need to have focus on this part first, and then I'll get back to that. Yeah.
Yes,
So we Biswa mentions, so we have to optimize the design of airfoil in such a way to minimize the drag and increase the positive suction more below the airfoil. Yeah, exactly, exactly. So it's not positive suction; it's like positive pressure. You can call it as a force we are acting. So if this is an airfoil, right? So it's you can consider this force I'm applying, right? So it's just increasing this force in order to lift the airplane. So yeah. Now, does anybody have any more questions? Because I am going to talk about angle of attack and how it is impacting what is stall, etc. Right? So yeah, before I go into the depths of that, I just wanted to clarify a few things for you before that. If anybody has any kind of doubt regarding what I have just mentioned, the being pressure being the drive force of the airfoil lift. In that regard, I'll be answering that question. Aditya said, "So, what is the material of Boeing wing?" I'll come to that. Yeah, I'll come to that. Yeah. So, if nobody has any questions, I guess I'll move forward. So,
Yes, sir, you can move forward.
yeah, okay. Now, we actually have talked about these parts, right? We have seen the pressure loading, the top suction surface, the bottom pressure surface, like what kind of loading or what kind of pressure behavior is there. Now we'll talk about integrated loading, right? So basically, the pressure distribution is essentially integrated to give a total force vector F. Now, that force vector F should be in such a way that it should be inclining towards the left side, and it should not be inclining, like basically it should not be more dominant in drag. It should be more dominant in lift. The reason is we want to lift off the airplane. So there are two conditions for this. Like one is the while you are actually departing the airplane, and while you are actually trying to land the airplane. So in the start of this airplane journey, when you are trying to fly it, your the most dominant force will be lift. And when you're trying to land it out, you need to have a proper balance with lift and drag force in order to get it safely landed without it being without introducing stall. So when you talk about this force balance, right? So your velocity component, basically the velocity that is directly incident on this airfoil, it is basically divided into two components, as I said, right? So your horizontal force that is being exerted by the air on the airfoil is going to generate drag, and whatever the air that is going to move past here, and it is going to move in this direction. So basically, when it tries to move like this in this direction, tries to generate lift over here, and basically your lift force is also generated. So this is how the force balance looks like for the plane. So the wing need to generate as much as lift to exceed the weight of the entire plane. It also needs to exceed the whatever the minimal whatever the drag that the plane is experiencing along with the weight that the plane has, and that's how it actually can counteract with the overall lift. So basically, you have your lift force in order to counteract the weight. You have your thrust that is being provided by the air jet engines in order to counter for the drag. So that's how basically both the forces are counteracted, and that's the general idea of the airplane lifting. So this is the force balance diagram for that. Now we talk about angle of attack. So basically, when you're trying to pitch before we move on to this, I just want to ask, yeah, what will happen, uh, or not what will happen? What should I do in order to generate more drag below? Sorry, in order to generate more lift force below this airfoil? What are the things that I can do? If anybody can answer that. Hello. Yeah. Deep Chawan says increase area of airfoil. Can you elaborate on that, Deep? Just tell me how can we increase the area of airfoil, and like basically how it is going to affect the. Manish says we can increase the speed. Okay. So if I increase the speed, that means I can generate more lift force. Is that what you're saying? Okay. Vedant says, sir, increase the thickness of airfoil for up to 15% max, more cambered airfoil. For Reynolds number over the airfoil, wings aspect ratio should be high. Yeah. So these are all advanced concepts, Vedant. I'm just trying to cover the basic crux of things. Like what is the most basic thing that I could do in order to counteract the different angle of attacks and still maintain or still generate higher amount of lift. Thrust is backwards or forward. Okay, thrust is forward. Basically, if this is your airplane, that means this is going to be your engine, and you are going to move in this direction. So basically, it's going to take the airplane forward. So thrust is forward. So yeah, thrust basically is an action which is okay. As an action, it is like the reaction of thrust is you are moving in opposite direction. So that's the general idea. And as increased area of an airfoil means more airflow come contact to the airfoil, and we have more lift. Okay, okay, that's good. That's good. Uh, yeah. So how do we propose we do that? Yeah, you can unmute yourself. It is I actually prefer you unmuting so that we can have a like general casual conversation. It's not like nobody's going to judge you or anything. It's just like knowledge sharing activity. People will.
So we can increase angle of attack.
Yeah, but before that, right? Let's say you don't have any awareness about angle of attack. You just want to know like how I can generate lift, more lift, making it more streamlined. Okay, okay, okay. So we have some interesting thoughts coming in. Yeah, great, great, great. So yeah, let me get back to that and let me share how we are going to generate more lift. Yeah, this one way I'm going to talk about. So we have the angle of attack in play. So basically, when you have your angle of attack set in this direction, so let's say my so let's understand what angle of attack is first. Let's say my air is moving in complete like horizontal direction like this. Yeah, and my the aerofoil is in this direction, like it's normal to that the nose of the aerofoil. This is basically called as a nose of the airfoil. This is a tail of the airfoil. Okay, and this nose of the airfoil is directly, basically the air is directly perpendicular to or is incident on the nose of the airfoil. Yeah. Now, when I actually try to lift my airfoil, or basically I try to tilt my airfoil in this direction, what I'm doing is I'm trying to increase my angle of attack, right? So basically, when I do that, the air is in this direction, but my nose direction is this. Yeah. So the angle between the tip of the nose, like the alignment of the airfoil with the uh, angle with the direction of the air incident on the airfoil is basically angle of attack. Now, when I try to move my airfoil, or when I try to pitch my airfoil in this direction, right, in this way, what happens is more air flows below the airfoil and less air flows above the airfoil. What happens is, due to the excess air that is flowing below the airfoil, it is basically generating more amount of lift over here, and that's how you, the that's how the lifting mechanism generates. So basically, when you are starting the dispatch of the airplane, right, when you have achieved the optimum speed on the runway of the airplane, when you're moving in that at that speed, the airplane configuration or the wing configuration changes in such a way that it tries to pitch the airfoil in the slightest or optimum angle of attack, and that basically allows more air to flow below the airfoil, and that's how it basically tries to flow away. So that's the basic essence or basic concept of the angle of attack. Now, what will happen if I increase the angle of attack too much? Because you must have a doubt, like, why don't we then increase the angle of attack as much as possible, and still the airplane will try to move upwards, right? So, can anybody tell me what will happen if I put my aerofoil in this manner? So this is my horizontal air, right? And this is my nose, like the perpendicular. I'm sorry about my drawing skills, but yeah, this is my the nose direction, right? The alignment, nose alignment, and this is going to be my alpha angle, right? Angle of attack. So what if I do this? What will happen? Can anybody tell me? Because essentially, if my theory is like, if I try to increase the angle of attack, that means a lot of air is going to move below the airfoil, right? And that basically generates higher lift. So this is going to generate a lot of lift, right? So what could be the effect of if I increase my alpha angle to this much? Can anybody tell me? Advait says, sir, at higher angle, the airfoil will stall and lift will decrease. Okay. Can anybody unmute themselves and tell me?
Hello.
Yes, Pratham, yeah.
Yeah, so it will increase the amount of stall
Okay.
and could cause in a huge amount of drag also.
Okay. So can you explain it to me or everyone here, like how it does that?
Mm, so basically, if we keep on increasing the angle of attack, so the airflow and the surface of aerosol will keep on increasing the drag, and as we increase the angle of attack, so it could be detached also with the huge amount of pressure and air pressure.
Okay. 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 Yeah, that's actually a great point. I'll show everyone that what Prathamesh said exactly in just a moment. Srujan says increase in angle of attack results in increase both and lift and reduce drag up to a point. Chandan says thrust will decrease. Aman says max air flows downwards and increases drag. Okay. And yes, says airfoils are designed for climax or for CL max. I'm not sure what the word is. If we further increase the CL max, the okay, coefficient of lift. Okay, coefficient of lift, maximum coefficient of lift. If we increase the basically it will cause stall, and there will be flow separation causing weight. Okay, yeah. So yeah, all of you have valid points. I will show everybody, for everybody's sake, how basically it is done. Yeah? So when let me just erase some of the things. Next. So when I have my airfoil in this angle, okay, basically due to this this position, as you can see, the air incident on this shape, the horizontal air incident on this shape will increase the drag in the horizontal direction. Basically, your force F vector will be more dominant towards drag. In this particular case, your force vector will be, so if this is your drag, then your force vector will be more dominant in that direction. So this is your F, and this is the drag force. So when your force vector F is in more like more dominant with the drag, basically your airfoil starts stalling because there is not enough air going from the upward side to maintain that lower pressure regime that we had initially talked about. All of the air is like most of the air is trying to move below the airfoil. That basically tries to increase the drag, and that's how your aircraft fails. So basically, that's how the lift fails. So this is the biggest consequence of increasing the angle of attack too much, and that's why we need to have an optimum angle of attack for providing the smooth operation and to generate the optimum lift that is required for airplane to lift. So this is how these are the few of the elements that are being used to actually stabilize the airflow or to stabilize the aircraft flow while it is in the air. Now, so basically this is the effect of that what we have just talked about. So basically when your angle of attack becomes too large, then the airfoil starts to stall, and that basically that increase of drag, that decrease of the airflow on the upper side of the airfoil basically classifies as stall. When your drag increases, your stall also increases with the increase of angle of with the increase of alpha angle. So when you try to draw a graph with angle of attack and the lift force that is generated or required, you can increase the angle of attack up to a certain point where you will get, so basically that's this point, you will get maximum lift for that optimum angle of attack. And beyond that angle, basically that's your critical angle of attack. And beyond that angle, your airfoil will start to stall. So it actually depends on what sort of mechanism, what sort of flow regime you are trying to implement. Now, based on this ideology, based on the basic understanding of aerodynamic design, there are a few of the shapes of the airfoil that are used for different concepts. Okay, so you have so I will not go into depths of these three shapes because I need to talk more about this last shape. Okay, and this actually brings me to the point of connecting this to the Boeing aircraft and why it is more efficient, the Boeing 787. Yeah, so when you talk about this airfoil design, this design is basically optimized to work or to extend the critical Mach number operations. Now, when you talk about aircraft flight, you need to be your flow needs to be in subsonic region all the time. If your flow becomes supersonic, then that case, or the airflow becomes supersonic, in that case it will generate a huge shock wave. Now that shock wave would generate like it will generate drag, and heavy turbulence will be generated. You'll feel heavy turbulence being generated throughout the aircraft, right? And that might increase complications. It might actually cause a crash. Okay, so why that happens? So when we talk about the airflow moving past this airfoil structure, right? We have been taking this airfoil as an example. So when you talk about air moving past this airfoil, even if your aircraft is moving at a reasonable velocity, which is well below the subsonic regime. So basically, those who don't know about subsonic supersonic differentiations, subsonic supersonic differentiation is made based on a number called Mach number. So when your velocity is comparable when the velocity is Mach number is basically a ratio of your velocity with respect to the velocity of sound. And when that number reaches 1, basically it means that your velocity is equal to the speed of sound. Yeah. So when your Mach number is equal to 1, when your Mach number is equal to 1, you are basically in the transonic state where you are slowly moving forward from subsonic region to supersonic region. Yeah. And the biggest problem, what happens is when your air tries to move past this point, even if you are under subsonic region, even if your Mach number is less than 1, the air that is trying to move past this point is accelerating. Okay, it's accelerating independently, and due to that acceleration, sometimes it might go into transonic state. Sometimes it might go into supersonic state. So what will happen is, in supersonic state, there is kind of a shock wave is generated when a flow regime tries to move from subsonic region to supersonic region. So basically, what happens is there will be a barrier, like air barrier, you can say, is generated, and due to this air barrier, your flow is separated now in this case. So basically, when your air is moving in this point, it is fine, but beyond this point, it becomes very turbulent. Okay, and due to this barrier, your the lift that is the aircraft that is stable, it tries to basically, due to this turbulence, heavy turbulence being generated towards the back end of the airfoil, it introduces heavy drag, and due to that heavy drag, your basically system it becomes unstable. Now, in order to counteract this, the updated design is basically this. Okay, so this airfoil is also called as supercritical airfoil. There are like a few minor changes in the design, so it's not like exactly like this. So the one that NASA has developed is something like this. Okay, so this shape is essentially called as supersonic or sorry critical Mach, or you can even call it a supercritical airfoil shape, which is basically used to calibrate or avoid this kind of instances. So what this shape does is, being the top of the airfoil being flat, it basically tries to keep the airflow in check, where it does not accelerate too much. And in order to counteract the lift portion, right? So due to this sharp change at the bottom, basically here you will have negative suction. But due to this sharp change, when your air tries to move past this region, it will in turn going to generate more lift. Yeah, basically it will generate the amount of lift that is required to lift that aircraft. Yeah, and this concept, basically this shape is critically optimized, where using this shape, the Mach number never exceeds beyond 1, or basically it remains in a subsonic regime, a subsonic flow. And even if it goes beyond the in the transonic state, what happens is your shock wave size is that was this much big due to the extensive acceleration, it becomes reduced, and because of the flat surface, because there is not much acceleration happening, and uh, even that less turbulence is there, you can easily able to manage and stabilize the aircraft. Now this exact concept is being utilized. Touch it off. Yeah, so that we can move forward. Escape. So, in the latest Boeing 787, says supercritical effort has geometric features as flat upper surface, round leading edge, high camber at the bottom right of the airfoil. It is used to increase the drag divergence Mach number, and also used to decrease the wave drag. Exactly, Vedant. So these are a few of advanced concepts you might come up. I'll be talking more about the shock waves and etc. things in the next session that I'm going to have in the next week, which is essentially a continuation of this part where I'm going to talk about supersonic flow. So there I'll try to cover as much as possible in that regard. But yeah, till this point, if anybody has any questions, any doubts, they can ask me. Did two things. Mainly, it reduces the weight, due to which the lift, counteracting the lift part is much more easier. It flew faster. While designing the wings, right? So the wing of the Boeing aircraft has a rib cage kind of a structure. Okay. So when you try to lift it, your whole wing itself tries to kind of bend. Okay. So previously, when this kind of bending was tried to integrate it in the aircraft, in order to facilitate smooth lifting or more lifting at the start of the flight, it was very challenging, because in order to bend the whole wing, right? It used tremendous amount of force. It required tremendous amount of force in order to do that, and due to that kind of limitation, this Boeing 787 actually has reduced or minimized, where the rib cage is basically made from carbon fiber resin alloy, and also there are the rib cage or the chassis of the wing is basically made from the aluminum integrated ribs as well. So basically the structure still holds some like for the stability, aluminum, solid aluminum is used, and for flexibility and to incorporate more bending, carbon fiber is used to construct it. Yeah. So this is one of the key advantages of. So, but yeah, so according to the thrust that is provided to the aircraft, so all of these things are counted step by step, and that's how this Boeing 787 aircraft is emerged. So this is the biggest advantage the Boeing 787 has, and that's how it essentially has the longer flight duration. It has longer blades or longer wings, and the one more thing towards due to this longer shape, or the size of the wing is basically longer because the weight is calibrated, right? So weight is reduced due to less heavy material is being used. So they can actually increase, or they have actually increased the size of the wings or length of the wings. Now, due to that, what happened was, so basically, if you consider this wing, okay, the longer your wing is, the less vortex are formed towards the trailing edge of your wing. So at this section, due to the longness of the airfoil, the air being flowing below the aircraft, below the wing, we have essentially increased the area of the wing, right? And that's why we have minimized the vortex towards the trailing edge that is being formed, which is basically also introduces a form of drag in the flight mechanism. So these are some of the key advancements or key features that Boeing 787 has, and that's how the Dreamliner is come to play, where it's the biggest, it's the cutting edge aeronautical advancement still there. So that's the general idea about the Boeing 787, and yeah. So that's the general idea about everything. Now, if anybody has any questions regarding Boeing 787 or anything that we have just discussed about, they can ask me. Yes, Rupali, do you have any more questions?
Only about Dreamliner, sir.
Okay. Yeah, yeah, you can ask me, no? So if there are any specific questions from you, I can try to answer them. Okay.
Sir, can you write a wingtip?
Hello.
Can we write wingtip of 787?
Wingtip. Actually, I'm not getting the question. I think there is some. Can you please repeat? Oh,
So this is specialization in Dreamliner, Boeing 787.
uh-huh.
Dreamliner, we can rate wingtip.
Yeah, I'm still not able to.
R-A-K-E-D. R-A-K-E-D. Wingtip. W-I-N-G-T-I-P.
Wingtip. Is it? Still, I'm not able to understand. Can you just put the question in the chat box so that I can understand?
Sir, wings are swept upward direction.
Yeah.
Exact wingtip.
Yeah.